All right. How's everybody doing? You doing okay? Not you guys are shaking your heads. I'm sorry to hear that, but I'm happy to hear those of you who said yes that you are doing well. Um, it's second week and it's already Wednesday. So um, this week, well, today I will cover gradient descent. We mentioned gradient descent on Friday, and today we'll take a look at gradient descent for linear regression, just to kind of get us familiar with the concept. And then on Friday, we will introduce neural networks. And I'm really excited for neural networks. I've posted some playlists on YouTube for you guys to watch. I hope you enjoyed the linear algebra playlist. That was good stuff, right? And then these neural network playlist videos are also good stuff. So we'll take a look. But anyway, let's talk gradient descent. Okay, gradient descent is just an iterative method to minimize a function. And basically, the rule is find out which way is downhill and take a step downhill. And keep doing that until you are at the bottom of the hill. Okay, so it's just basically keep taking steps downhill. Okay, until you are at the bottom. Gradient descent will get stuck in local minimums. So that's that. And there's not even guarantee that it'll converge or anything like that, right? So these are just, it's useful in its simplicity, but it's not guaranteed to work, okay? But so just some warnings, right? Buyer beware. And let's just review the gradient of a function. Points in the direction of steepest descent. Okay, sorry. And then so going in the opposite direction would point in the direction of steepest descent. Okay, and then so if we plot a function in 2D space, the gradient is perpendicular to tangent lines of the contours of F. Okay, so for example, we might have, again, some kind of paraboloid. And if we plot this, it would look something like these are supposed to be. Is there a word for concentric, but when they're not circles but ovals, ellipses? Is it still what? Concentric? Concentric ellipses? Is that even a thing? Huh? Nested ellipses. Okay. Yeah, okay. Well, anyway, we have some kind of, we have a tangent line here, and I can't even draw. Okay, and then, and so this would be, this is, all right, so this is supposed to be perpendicular. This would be the direction of the gradient, okay? And so we just go in the direction opposite of the gradient. And as we, this looks terrible, but as we get, these are supposed to be a bunch of little arrows that converge to the center, or the bottom point there. Okay, and all we do is, and basically gradient descent. The algorithm is this, you know, start at some location, and then your next location is where you are after a small step, or where you land after a small step in the direction opposite of the gradient. Is that all right? So I'll do gradient descent first with the gradient as partial derivatives, and then we'll do gradient descent in matrix notation. And it works either way, okay? All right, so we'll do gradient descent where we calculate the gradient as partial derivatives. Okay. So our gradient of the loss function is going to be equal to the partial of the loss with respect to W0 and the partial of the loss. Did you feel that, or is that just me? Maybe something is happening behind. It felt like an earthquake and I got scared for a second. But nobody else was bothered, so I'm just having a slight heart attack right up here. But story of my life. Okay. So this is what we have, right? Okay, so keep in mind the loss function is basically will be the mean squared residuals. Okay, so and we're doing this for kind of the vector where W0 is the intercept and W1 is the slope, right? Okay, so we're going to take the gradient with respect to W, and so we'll start with the gradient with respect to W0. So this will be the partial with respect to W0. And then the loss function is 1 over n, the sum of n equal to 1 to capital N of Tn minus W0 plus W1 xn quantity squared. Okay. And so if I take the derivative of this, I can just apply the chain rule. I don't even have to expand it out. I can just apply the chain rule, and I'll get 2 times T sub n minus W0 plus W1 xn multiplied by the derivative of what's on the inside, which is just going to be multiplied by -1, right? Okay, and then just kind of just rearranging some terms, I get -2 over n times the sum of n equal 1 to n of T sub n, and then I'll just distribute the negative W0 minus W1 xn. Okay, that is the gradient, the partial for W0. And then let's do the same thing for W1. Okay, so I get dW1, 1 over n, sum of n equal 1 to capital N of T sub n minus W0 plus W1 xn squared, and again, just doing the chain rule, 2 over n inside times negative x of n. Okay, and so here I get -2 over n Okay. Is this okay? All right, and then, so then the gradient descent algorithm will be that we're going to say is W at time n plus 1 is going to be just take your current, the gradient, your estimates of W at time n plus 1 will be your current estimates minus just a small step in the direction opposite of the gradient, right? So we're just taking this. So that just basically means that W0 at time n plus 1 and W1 at time n plus 1 is going to be equal to W0 at time n minus some lambda times the partial at W0, and then W1 at time n minus some lambda times the partial at with respect to W1. Okay, and this is all we do. So all I'm doing is I'm saying we're going to take our current W0 and our current W1, and then we've calculated what the partial is. We got to plug in a bunch of numbers to get this, and then we'll just update the next iteration with this. Okay, and then all we do is we just repeat. So just keep taking steps until we decide to stop. All right. Is this okay? Any questions on what I've done here with the partials? Okay, and then I'm gonna go ahead and I'll code all of this up. And I think I put this on CCLE if you wanna open it up, or we'll just take a look at it in R here. So this is with partial derivatives, and let's see. Is this the one? No, this is vector notation. Okay, so here I'm going to just use a very small I gotta resize my window. Yes, question. Hello. Okay. Does that fit? Yeah, it does. Great. Okay, was there a question? We're okay? All right, so here I'm going to just, we're going to start and I'm going to create, so this is all we're trying to do. Let me just plot my x vector against my t vector. Okay, this is what we have. And then if I fit a model, I could do AV line LM t vector as explained by x vector. Okay. Okay. And this is all we're trying to do, right? And then if we wanted to know, if we did linear regression, it tells us that the coefficients, the intercept is 1.8 and the slope is 3.1. Okay, so I just have these three data points and we're trying to fit a linear model to this, okay? But we're not gonna use the linear model function. We're gonna do this ourselves using gradient descent. So we're not even gonna, so it involved us finding the gradient, but we're not going to even try to set the gradient equal to 0 and solve for where the gradient equals 0. We're going to apply gradient descent, which just says start somewhere and then keep taking steps in the opposite direction of the gradient, okay? So we're not solving things, we're just applying the algorithm of starting somewhere. So here, I'm going to calculate the loss, which I've called the loss for non-vector, because next we'll do the same thing in vector notation. And so this is just going to calculate the loss, and all I'm doing is I'm just taking the current loss, which starts off at 0, and it goes through every point that I have, and there's only 3 points here, but it's going to just take the value of the second value, basically the y or the t, and subtract off the estimate and then square that. So the loss function is just, here it's the total sum of squared error. It's not 1 over n, but as according to one of your homework problems, you'll see that the optimal solution for total sum of squares is the same as mean sum of squares, right? So here, the loss function calculates the total sum of squares. And I hope this, I'm not really going into the function, but it just takes, it's adding the loss and then it's calculating the residual squared and it's adding it to the loss. And it does that for all the points and it returns back the loss, right? So currently, if I fit in the points and the intercept 0 and the slope 2, the loss is 87.77, okay? Which is probably not, let's just see what that looks like. AB line 0, 2, color equals red. So that's if I fit this line 0, 2, this is the kind of loss that we would get. Okay, we calculated the gradient, and I hope I did the same math here. Is we're doing the gradient with respect to W0 is we're going to add up for all the points t sub n minus W0 minus W1 xn. Okay. And so we start off with the gradient, and then -2. Again, I guess I got rid of the 1 over n term. But we're going to take the t sub n, okay, which is for that point, minus w0 minus w1 x sub n. So this is basically what this part is, okay? And then the fact that I'm going to do the loop through all of the points takes care of the summation here. Is that okay for the gradient for w0? Same thing for w1. w1, it's -2 times, and then it's the sum of x sub n, t sub n minus w0 minus w1 xn. So I have that -2 times the point for x times t sub n minus w0 minus w1 times x sub n. Okay, or I guess in this case it's I, and then we sum them up because we're running the loop for all the values. Okay, and then so I get the gradient for w1. Okay, so I have two functions where if I plug in the points and then our current values of w0 and w1, it calculates the gradient for me. Just make sure. Okay, and then now I'm going to plot some contour lines. So here I'm going to just create a range from -1 to 5, and then 1.5 to 4.5. And so if I plot the contour, I'm just calculating the loss function for every value in this contour, and then I'm going to just create the contour plot, and this is what it looks like. Okay, so this is what the contour plot looks like for different possible values of the slope and intercept. So far, so good? Okay, and so here I'll start off with some initial point, -1 and 1.5. We'll start off with the intercept, -1, and the slope, 1.5. Keep in mind that the optimal value has an intercept of +1.8 and a slope of 3.1. Okay, so these are wrong, and I'm going to just create a matrix to store all of my values. Okay, and so here I've got, we're going to start off, just have an empty matrix. Our first row in the matrix, so if I just do head of the matrix, is our initial plots of -1 and 1.5, and then everything else is missing, okay? And then all I'm going to do is each step is just going to be alpha times the gradient, okay? So I'm going to do step for w0 is going to be alpha times the gradient at that point. Step for w1 is going to be alpha times the gradient at that point. And then the next value that we will keep is going to be our current value w0, and then we just take a step in the negative direction, right? Minus whatever that step is. So we're just subtracting off whatever the gradient was calculated to be. And then once we get that, we just plug those values into our W matrix, and then we update this, and we just repeat the loop over and over again. So we do this 500 times. Okay, every single time, just calculate the gradient at the new location, take a small step in the direction opposite of the gradient, and then update and redo it again. That's gradient descent. So there was no solving, we didn't set anything to 0, and we did that. Okay, now it's done. All right, we can kind of see, you know, how close did we get? Let's just take a look, tail at our W matrix. Okay, and again, the optimal values are 1.8 and 3.1, and so we got close, not perfectly there. Probably if I ran it for many more iterations, we would get closer. But that's fine, okay? So here's our contour, and then let's add kind of the trace of our thing. And so what all we're doing is we just started off at -1, 1.5, and then we just took steps. And at each point we can see it's kind of perpendicular to the contour lines. And we get to a point where, you know, we start, and, you know, right around here is when we start to make a, you know, a turn, and then we go, and then it converges or gets very close to where the minimum is. Okay? We can see a few things. If I were to change my step size, learning step, to something bigger, and I just reran this. Well, I guess we can do this with the matrix notation. Let's just redo this. We see a little bit of funny behavior, okay? And what happened here is that at a certain point, the next step was a little bit too big, and it overshot. It overshot where it was supposed to go, and so it ended up over there. It takes a step perpendicular, and it overshoots again. It overshoots where it ended up, and so, but it does work, and it kind of it still works out. Okay, but that could happen, and again, it's hard to know what value of alpha you should choose. If I do take an even smaller alpha, our steps here, and let's just take a look at the tail of our W matrix. And here we got very, very close to the true value of 1.8 and 3.1 with the slightly larger steps, even though I kind of overshot. Here I'll take really small steps, and so I probably won't converge to the final location, but so we'll just see what our tail looks like. Yeah, so we're not that close, but let's just kind of plot and see what happened. That looks pretty much the same as the first one we did, but the steps are even smaller. Okay. Okay, is that okay? Gradient descent. All right. Let me show you the same thing in matrix notation, and I think the matrix notation solution is more elegant, but you know, maybe we disagree. You could imagine that if we had more than just an intercept and slope term, but like a multiple regression thing with 5 terms or something, doing this partial derivative method could become very tedious because you got to find the partial derivative for every single term, right? So so we don't really, like, we didn't do it with 5 different partials. So you don't get to see the total tedium, but you could imagine it. Let me just show you gradient descent. Something happened. I think I clicked the wrong button. Okay, let's try this again. Gradient descent in matrix notation. Right, and I think this is more elegant. But I guess you have to be comfortable with matrices and stuff. Okay, so basically the gradient descent algorithm will be that the next iteration of W is going to just be our current slope and intercept and slope minus lambda times the gradient of the function at our current value. Okay, and I guess in this case f is our loss function, so if you want to write L instead of f, then that's fine. So in matrix notation, our loss function, I'll keep the 1/n's here, but I think we established this in matrix notation is going to be t minus x W transpose times T minus XW, right? So we got rid of the summation because now we're in matrix notation here. Okay, and then if we expand this out, we've got T transpose T minus 2 W transpose X transpose T plus W transpose X transpose X and W. Okay, so this is our loss function in matrix notation. Okay, and then now we will just find the gradient of L with respect to W. And so if we can take gradients with respect to W in matrix notation, we just get 1 over n. This thing becomes 0, right? And then in here I get 2 X transpose T. Okay, and then here, this is basically W some matrix times W, and so I get 2 times that matrix, X transpose XW. Okay, and all I'm going to do is I'm going to just rearrange the terms, but this is it. This is the gradient with respect to W. Okay, and so just rearranging terms. Wait, let me just take a quick peek just so that when I look at the code, the gradient looks exactly the same. Okay. X transpose negative X transpose T plus X transpose XW. Okay. So here I get negative X transpose T plus X transpose X W, and we'll multiply this by 2. That's what we have there. Oh, I'm sorry, 2 over n. Okay, and so that's the gradient right here. And therefore, the next value of Wn plus 1 is going to be exactly this, W sum n minus, well, I guess I'm just ending up copying this, but times the loss with respect to W sub n. Okay, so no partial derivatives to mess with. We just leave it in matrix form. This here is the gradient of L with respect to W. Okay, so now I will implement this in R. Just all I had to do was calculate this as the gradient, okay, and then this is going to be my total loss, is this up here. So in matrix notation, okay, so I'll start off, let me just clear my environment. We'll start off again with this same 3 data points, 1, 3, 5, and then the X matrix now is, a column of 1s for the kind of the intercept term, and then 1, 3, 5 for the X term. Okay, and we could solve for what the optimal value is, 1.8 for the intercept and 3.1 for the slope. This is kind of, in a sense, quote, cheating, because that's not what we're doing here. But we're not going to use that, okay? And so the loss function, again, is t minus xw transpose times t minus xw. So all we have to do is just put this in matrix form. I just have t minus xw, x times w, the entire thing transpose, times t as a matrix minus xw. So this is going to be the loss function. And what do we use for the initial one? What we had the back. Okay, so if I plug in 0, 2, I should do that. 0, 2. Okay, we can see that calculating the loss function gives me the same result as I did, well, way back when, right? And then if I plug in the optimal values of the w vector, the loss function is very small at 0.06. Okay, so that's what we're going for. Okay, and then the gradient of the loss function is just exactly this, is negative x transpose t plus x transpose xw. So that's what I have. I've got negative x transpose, so t of x times t. So negative x transpose t plus x transpose xw. Okay, and I guess I threw away the coefficient 2 over n, but as far as what the gradient goes, that's what we have, right? Negative x transpose t plus x transpose xw. That's what we have, just for the gradient. So the gradient, to calculate the gradient, we just plug in the current value of w into the function, and we get the gradient of the loss function. Okay, and then so if I calculate the gradient at the point 1.8, 3.1, this is the optimal solution. It returns back, the gradient at that point is basically 0, 0. Okay. Whereas if I plugged in not the correct value, the gradient at our current estimate, it tells you this is the gradient at that point. Okay, and then so if you wanted to just do gradient descent without graphing any of it, all you have to do is you just start off with some arbitrary point. So here we'll just start off at 0, 0. I'll pick a small lambda, and then I just do a bunch of iterations where I take my current vector for w and I subtract off lambda times the gradient. Okay, and then when you do that, you see that it converges very close to the actual solution. Okay, that's all you have to do if you just want to do gradient descent without plotting any of it. If we want to plot it, make a nice little picture, we can do that as well. So all we have to do is we'll just graph our, I think I'm using the same loss function from before. I didn't bother coding it up in matrix form, so I'm just plotting all of this. So here's my contour plot again, okay? And then and I'm just creating an empty matrix to record all of the values, okay? And then now the gradient descent, you can see, is much simpler here, right? So in the non-vectorized form, I had to do each thing, but here all I have to do is just say take our current values and then put it into the row here, and then the next value is going to be the current w vector minus lambda times the gradient. Okay, so this is the gradient descent right here. It's a lot smaller when you keep it in matrix notation. And we're done. And then if we want to plot this, we see it indeed worked, okay? In that it follows the gradient and then gets to the point going perpendicular to the contour lines until it gets to the central point down here. And we can see kind of the tail of our W record matrix. And well, I guess it's not, maybe it's not as close as I thought. But, you know, getting closer, I should probably run it longer. Maybe 1,000, who knows? Okay, and then let's just take the tail of our... Okay, so it's a lot closer, although the final plot looks the same. Okay, again, we can just kind of mess around with what happens if our lambda step is too big. We can plot this, and we can see, you know, we overshoot and we take steps that are too big, and so we bounce back and forth. But eventually we get to a point where we converge down to the central point, okay? So, you know, in my opinion, and the doing it in matrix notation, calculating the gradient in matrix notation makes the coding easier and more elegant in that gradient descent really is just W minus lambda times the gradient here, okay? Because the functions are working in matrix form rather than having to have a separate function for each partial derivative for W0 and a partial for W1 and a partial for every single term. You know, if we're comfortable working with things in vector and matrix notation and taking the, you know, kind of derivative or gradient in vector form, we can do this, okay? And again, the beauty of gradient descent is that nowhere did we have to say the gradient is equal to 0 and solve for where the gradient equals 0. All we did was just say, we're starting here, we can calculate the gradient, and the gradient is pointing this way, so we're going to just take a step in the opposite direction. We're going to just keep walking downhill until we get somewhere near the bottom, okay? And this is going to become very useful when we do neural networks, because the function ends up being really crazy, the gradient is going to be really crazy, and it's not easy to solve for where the gradient is equal to 0. It might not even be possible, okay? So, you know, with linear regression, sure, setting the gradient equal to 0 and solving for that, that's an easy thing. With a neural network, you find the gradient, but then you can't set it equal to 0 and solve. So instead, you just start out at some point, and we say we can find the gradient, and we're just going to start walking downhill, and we're going to do our best, okay? So on Friday, I'll introduce the kind of the overall concepts for neural networks, and I think it'll be pretty interesting. I'm really excited. If you've got the time, please be sure you watch the Welch Labs playlist on neural networks, and then if you have additional time, check out the ones by 3 Blue 1 Brown.